Now, do you remember last lesson I said I would explain more about why we get a specific emission spectra for each element, but I said I'm not good at making words and I want to write it down and come back to you with that. Yes, I did that. Okay? Okay. So, explanation. I'll make that font a bit bigger. Emission spectra and why only certain frequencies of light are emitted. So I went away and did a bit of reading and put it together. Is that font large enough? Bit bigger? We go one size more. Okie dokie. Ready?
Yes.
Now, what I have written here, is really 3 points. The first thing is about the excitation process. So, excitation promotes the electrons to higher energy levels, and on return to the ground state, the energy is emitted as light. Okay, next. Why are there only certain lines? Why are there only certain lines in the spectra? Because electrons can only inhabit, which means be on. Oh, I haven't started recording. Electrons can only inhabit quantized, which means a limited number of energy levels. So only certain color frequencies, not wavelengths, are observed. Okay? Quantized energy levels means a certain number of energy levels, a limited amount, not infinite. Yeah?
Is that because there's only a certain amount of electron shells can jump to?
Yeah. And like a bookshelf, you can't put a book in between the second and the third shelf. It can go on the second shelf or on the third shelf. The distance between those is constant. Okay, so the shelves are like electron shells.
I mean, books are kind of in
Whatever. Let's not start. Stop. Do you understand what you've written or what you are writing for that sentence?
Yes.
It makes sense? Okay. And are you ready for the next sentence? Yes? Okay. This is another important sentence. The difference in energy levels is different for different atoms.
Not liking these differences, but you've got to change it there. Not cash money.
Can you just click synonym? Like right-click synonym for one of them, please?
Where's synonym?
Oh, you don't have
I love cinnamon.
There's not one on there.
L.
It's only on Word.
The difference in energy levels is different for different atoms. It's not that bad.
Pretty bad.
Change is
Change.
a kind of unique word.
No, for each atom.
Oh, wait, unique. For
Varies for various atoms.
Varies.
each also just
Okay, if whatever. So, emission spectra can be used to identify elements. All right. What is ionization energy? It is the least amount of energy required to ionize an element. Specifically, to remove the most loosely bound electron. Okay? So it's the amount of energy required to remove an electron from the outer shell. Does that make sense?
Yeah.
That is what ionization energy is. So we can see here an example of magnesium losing its outermost electron And this here is showing us that it would take approximately, well, it's kind of exact, 733 kilojoules of energy.
How do we give it?
So let's have a little look at what the ionization energy is. So the first ionization energy is the energy required to remove the first electron, yeah, to give it a 1 plus charge. Yeah? Okay, so you can see how this varies for different elements on the periodic table, which is listed there. Okay, if we plot that, it looks like this. Okay, what you need to be able to do is explain the trend. Go, Pat.
Why is bromine, like the B, why can that lose it easier than old beryllium?
That is a fantastic question, Patrick. Why can bromine lose it easier than the old beryllium? Because let's write out the electron configuration for boron and the old beryllium. So it's going to be 1, let me press that old draw button. 1 S2 for the first shell. And then we're going to have, no spoilers, 2 S2, 2 P, where's boron and beryllium? Oh, I've gone too far. No.
Yes.
Okay, so that's beryllium, which has 4 electrons. Boron has 1 S2, 2 S2, 2 P1.
And so the P1 is like no good.
Well, it's just its little lone electron all by itself in the P subshell. Okay? Whereas our S subshell is full, and we know that fullness means stability, right? So the S subshell is full, that's relatively stable. Whereas the P subshell, there's just one little electron in there. So it is easier to remove one from the P subshell than one from a full S subshell. Does that answer your question, Patrick? Is that what you said?
Bloody checks.
No.
Does that make sense?
That's just a reactivity thing.
Sort of, yeah, sort of. All right. What else do we notice about the trends? I like that you identified that one yourself, Patrick. Who else has something to mention about the trend?
It goes up and down.
It goes up and down.
It's like the same pattern.
When it goes from like a noble gas to an alkali,
It's like the same pattern.
Okay, and why does it take so much more energy for the noble gas compared to sodium?
It's not really electrons.
Remember never to use the word want, but yes. So for neon, we have a full valence shell, don't we?
Yeah.
For sodium, we've got 1 electron in the valence shell. Not only that, but it's much further away than neon's valence shell, isn't it? Because it's an extra shell after neon's valence shell. Okay? So there is less electrostatic attraction. Are you even listening?
Yeah. There's less electrostatic attraction.
Yeah? Do you know what that means? Do you know what I'm saying? Related to the rest of the things? Are you with me? Really? Okay. All right. So, much easier to remove one from sodium because it's it's 1 electron in the third shell. It's only 1 electron in the third shell. Much easier to remove from a second full shell. Also, the third shell is further away from the nucleus than the second shell. So it's easier for that reason too. Which is why it's easier to remove from argon than from neon. Yes? Because argon's valence shell is the third shell. Neon's is the second shell. So further away, easier to remove an electron.
Does that mean that it's easier to remove something from the third, like the P subshell, than the S subshell?
Yeah, theoretically.
But not.
Because the P is at a higher energy level. Yeah.
Yeah.
Okay. Does that make sense? why these increase is just because of the increased number of protons in the nucleus. So the difference between fluorine and oxygen, for example, much easier for fluorine because,
Surely it's much easier for oxygen.
oops, yep, oxygen's lower down. Easier for oxygen because oxygen has one less proton. So that's less of a pull into the center. Does that make sense? Did you listen? Okay, well, it's amazing that it makes sense then. Okay. Shh. Continuing. Please watch. Okay. We don't only look at the first ionization energy, we look at the second and the third and etc. Okay? So first ionization energy is the energy required to move the outermost electron. Second ionization energy is the energy required to remove the next one once you've removed the first one. Yeah? Okay. So if we look here at beryllium, we can look at the amount required. So 899 kilojoules required to remove the first outermost electron. Okay? Required to remove the outermost electron. Slightly more energy required to remove the next one. And that's because of the increased proton to electron ratio now. So for this one, we've got 4 protons, 4 electrons. Here we have 4 protons, 3 electrons. Okay? So we've got a higher ratio of protons to electrons. So the pull on that outer one is now stronger. Does that make sense? There's not a big, it's a reasonable difference in energy there. Why is the next one massive?
Yes, out of shell.
What do you mean? Yes, it's closer. Yes. Yes? So this is from shell 2. These two are both from shell number 1. Okay? Now shell number 1 is much closer to the nucleus than shell number 2. Much greater electrostatic attraction, so much harder to remove an electron. Make sense? Okay? And much harder to remove the very last electron, because at that stage we've got 4 protons pulling in just 1 electron. So it's really holding that electron. Does that make sense? Cool. Why is there no 5th ionization energy for beryllium? Beryllium only has 4 electrons.
You said that that's the energy when you take one off and then you take the next one off. If you were taking 2 off at the same time,
You'd have to add those energies.
add them together. It's not like different because, no. Or is it not in the course?
It's not in the course. Also, we simplify things a lot numerically in chemistry. These energies probably vary from scenario to scenario, but we just put it down as this is the ionization energy all the time. But in reality, there's probably some variation and some different circumstances and things, but we just keep it super simple. No, you don't need to remember them though. Yeah, but you might get a question like this where it gives you these ionization energies. The question might say something like, why is the second one higher than the first one? Why is the third one so much higher than the second one? Or it might not say beryllium, and it might say, how many valence electrons does this have? And you're going to look for where the big jump is, and it's after 2 have been removed. So you can go, then it must be 2 valence electrons, because after 2 have been removed, the next one requires way more energy, indicating it's from a further in shell. So I run out of breath then. Questions on ionization energy. So I've taught you all of ionization energy, all there is to know. Let's do the questions now, which may answer more of our questions. Let's go.